Okay, so using first and second order integrated rate laws, we did an example with a first order integrated rate law, but to make all things equal, I guess we should make sure we can use a second order integrated rate law. So if a reaction follows second order kinetics, that means that the rate law is K times the concentration of our reactant to the power of 2. Let's see if I can tidy that up a little bit, make it prettier, just so you can see. So our rate of reaction is proportionate to the change in concentration squared. There you go, like that, kind of. Okay, so that's our second order rate equation. Okay, so what's our second order integrated rate law? So that is that the inverse of the concentration of whatever our reactant is at time t is equal to K times T plus the inverse of 1 over the initial concentration, which we'll call A0. Let me just tidy that up a little bit so it looks a little bit nicer. So depending on what you're solving for, depending on what you're rearranging for, this particular question is giving me the initial concentration, 1.21 molarity. It's asking for how long it takes for the concentration to decrease by 82%. So it's asking me to rearrange for time. So I need to work out what my concentration is at time t. So my concentration, or was it H3PO4? H3PO4 at time t is going to have decreased by 82%. So that means that is going to be 100 minus 82. It's 18% of the initial concentration. So I can just multiply my concentration of H3PO4 initially by let's see, 0.18. So where I'm getting that from is 0.18 would be 100% minus the decimalized percent that we're given. So the percent 1 times the decimalized decrease, right? So that's where I'm getting that 1.8 from. Sorry, 0.18. So we're going to take the 0.82. So 82% is 0.82. So it's decreased to 1 minus 0.82, which is 0.18. So my concentration of H3PO4 at time t is going to be, let's see, what was it, 1.21 molarity times 0.18, which is going to be about 0.1278 something molarity. So that's going to be my final concentration. Okay, or it might have just given me the concentration. This particular question, it made me work it out. Okay, so I've got to rearrange and solve for t. So I'm going to subtract 1 over A0 from both sides. So 1 over concentration of A at t. I'll just keep this generic for now, okay? Minus 1 over concentration A. Hello. A0 equals KT. So then I can just also divide by K on that side to get T by its onesies. So just times that by 1 over K, right? So T is going to be 1 over K. Get that to line up. Times by open big bracket 1 over concentration of A at time T. Minus, so you have to be careful with brackets, putting this in your calculator, okay? Concentration of A at time 0. Close brackets, thank you very much. Tidied that up a little bit. So now I can just chuck some numbers in and hopefully get the answer which I seek. Be careful with your units, etc. Should end up in seconds, right? Looking at my rate constant is per molarity per second, and my concentrations are going to be molarity. That's going to give me just seconds. But anyway, we will do the method. So 1 over K 4.82 molarity to the -1 seconds to the -1. Okay, let's space this out a little bit so it's a bit prettier. Something like that. What? Who am I kidding? I'm not going to make this look pretty anytime soon. Okay, and then times by 1 over. So again, you might need to do bracket, bracket, right? 1 over, uh, we just calculate 0.1278 molarity. Okay, let's make this prettier. So again, I would usually put this 1 over 0.1278 in parentheses, brackets, and I put my 1 over my 1.21 molarity in parentheses as well, just so our calculator can't stab us in the back, because calculators like to do that, right? So this is what we're going to put into our calculator. Okay, so molarity is going to cancel out, okay? And 1 over seconds is just going to be seconds, so it's going to give me time in seconds, and I got 0.78 something, blah, 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 seconds for that one. Okay, so there you go.